Никой път няма го правя на това. Не, Митра, ако беше он трябваше да почне на английски да говоря, ali ja нямам проблем с това. Как и да, значи, добре, прави малце на македонски, значи фала за Java, за PG Юг. PG Юг викате ви или Java User Group България? Джук. Да, Джук. PG Юг или PG Джук? PG Джук. Добре, мерси на PG Джук, ще ме поканя. Ги ве дръжам за фатре някои сад време венда. Ви кажа дека имам много време на разполагане, така да ги ве дръжам тука. Много битен слайд, значи ќе свъртам на английски. До тука, значи ќе виде. Може да разберете как ще говорам, само што проблем е дека има некои субтилни разлики помеѓу македонски и бугарски, посебно кај некои фрази. Пример, дали тука некој од вас пуши цигари? На бугарски пример вика пушеното е вредно за здравето. На македонски тоа значи дека е добро за здравето, значи дека супер е, значи, така да, ако пушите цигари, дојдете во Македонија, така таму се добро. Да, така да ќе продолжам на англиски. So, again. My name is Panče Javkovski. I'm a senior software engineer at Netcetera. We are a company based in Switzerland, and we have also offices in Skopje, in Bern, in Vaduz, and also in Dubai. Currently, I'm the Juke MK leader. I inherited Mite. Maybe Mite has been here before. I don't know. J Prime, yeah, he was here. J Prime last year. This year at J Prime, yeah. Okay, also I am one of the administrators of this coding competition that we're organizing for students, algorithmic competition, called CodeFu, MK, if you want to check it out there if you're into that stuff. Now, besides regular 9-to-5 programming, enterprise projects and stuff like that, I am pretty much involved into hardware, and I'm also a huge IoT enthusiast, pretty much into that world. Have a blog, panche.mk, try to write like a blog post in a month or something like that, if I manage to get the time. And on Twitter, I'm Silumedus. That's also my nickname everywhere on the internet, so you will see some links throughout the presentation. So, I have actually two parts of this presentation that I want to cover. The first part is this whole area of how, the Raspberry Pi area, doing hardware stuff with the Raspberry Pi, coding in Java, in JavaFX, and all that kind of stuff. And the second part is like an intro, like this hello world of all these smart home or Internet of Things stuff and everything. So I'll try to cover like the basics everywhere, but nevertheless, this should pretty much get you started, into the world here of hardware and Java, and also something else that I will mention. So, as the title is and as the content will be, I will talk about hardware. So, yeah.
Before that, just to say that usually it's forbidden to drink beer here. However, there is a beer over there, so you can grab it. It's free.
No, we are not forbidden.
Okay, so as I said, I will talk about hardware. So that means that I will not explain what the simple bits there are. So I'll try to kind of grasp on the bigger abstracts, on top of that. So that means that basically I will not explain how an LED works or what a resistor is or stuff like that. So let's start. First of all, Raspberry Pi 2. So this is one of the devices that I'll be talking about. Pretty much everyone knows here what that is. So it's a single board computer. It's based on this Broadcom system on a chip there. It has this 900 MHz quad-core CPU. It's based on this architecture. It's called ARM v6 v7. That is basically the instruction set. It's kind of important. You may want to remember that, because I just heard here someone talking about Odroid. Odroid C1, it was you? Yeah. Okay, so Odroid is based on the same architecture set. So that means that basically everything that I'll be talking about, the Raspberry Pi, Java on the Raspberry Pi, JavaFX on the Raspberry Pi, the same thing can be applied in the same manner on Odroid or any similar devices as is. Okay, so let's go on. So from all these out-of-the-box features that the Raspberry Pi has, well, at least those that are for the consumer market, let's say, it has hardware video support, so it's kind of like the perfect solution if you want to build your own home media server, stuff like that. Also, it has HDMI output, it has USB ports, 4 here, I think it's 2 hubs or 1, not really sure. A Ethernet port, audio composite, which is present there. But these are not the stuff that are interesting, or at least that are not interesting for me. I mean, if you just use them, you will have like a regular computer at home, which is a bit slow. It has a nice video rendering and stuff. The thing that we're interested in are the other stuff. So here, the first thing is the GPIO headers. So this is, let's see here, if if I can make this laser pointer. So this thing here, yeah, this big thing here. So it has 40 pins and it's called the main GPIO header on the Raspberry Pi. That is the one thing that we're interested into. The second thing is that the Raspberry Pi can run Java and JavaFX, and it can run native Java and JavaFX on that. So previously there were some ports, but they were based on Java 7, JDK 7, stuff like that, and they were buggy, they were slow, they were hard to run. Nevertheless, from JDK 8, there is an official supported version coming from both Oracle and from the OpenJDK, and it is specified solely for these architectures of CPUs. So that, as I said, ARM v6, v7 devices which have hardware floating point operation support. So if you have any of these devices, then you can run Java on it. So JDK 8, the Oracle JDK or the OpenJDK, they can run there without any problem. Even better, if you download the official supported operating system for the Raspberry Pi, which is the Raspbian, it already has the JDK 8, that is the Oracle JDK 8, it's already bundled with it. So you have Java, you have Java C, you can use them directly. So let's get into it. So again, this is the GPIO. Now the GPIO stands for General Purpose Input Output. And on the Raspberry Pi, the version 2 Raspberry Pi, it consists, the main GPIO header consists of 40 pins. On the previous version of the Raspberry Pi, the A and the B, but yeah, both of them, it has only 26 pins, and they are the same 26 pins you can see there, so around here. Now, the pins here are colored properly, and I think that I've matched the colors there. I think they're good. Now let's just pay attention that all the pins are marked into groups. So let's just through all these groups here. So the red ones and the black ones are for powering. So if you want to attach something like a different device on top of your Raspberry Pi and want to extend it, then you need to power it somehow. So you can see here that we have 5 volts and 3.3 volts pins, which we can use, and several ground pins that are distributed throughout the GPIO header. That's one. Next, the GPIO pins, these are the standard general purpose input-output pins. I believe there were the 8 GPIO pins for the first version and plus 8 for the second one, so in total 16, I think. Okay, and every single one of them can be used either as a digital input or a digital output pin. Now, here's a bit of catch, you don't have any analog input. So if you're used to coding in Arduino, say, and if you want to have analog inputs, to read something from the outside, then this is completely not possible here. Every single one of these GPIO pins can be either set to work as a digital output or as a digital input. So it can only work with one digital bit, that's it. The next groups are the interfaces that you will use in order to communicate with some third-party devices. So you have, in order here, you have the UART, which is basically the serial port. You have the SPI interface, I2C interface. Yeah, these are the 3 ones. And last but not least, there are these 2 additional pins that are added to the Raspberry Pi 2 that are dedicated in a way for adding an external EEPROM memory. But again, they can be used for I2C communication as well. So I will go into these interfaces a little bit more into detail. So, okay, so that is how you can actually connect something on the Raspberry Pi. So you have the GPIO header, you have the pins, you can connect their stuff. But afterwards comes the, well, let's say the part for which we are more specialized, the software part. So how can we actually code here? In order to access the hardware aspects of the Raspberry Pi in Java, then the thing that you need to use is the Py4j library. Now this Py4j library, it's open source by the way, this Py4j library is a GNI to this underlying wiring Pi library, which is written in C. So every single port that you have seen or you may have worked on, with the Raspberry Pi in any programming language, basically everything is based on this library, wiring Pi, and that is the only interface to the hardware aspects. So what can you do actually with this library? So first of all, you can export and you can control these GPIO pins. That is one of the stuff. So you can take one pin and you will say, okay, now I will use this pin as a digital output or as a digital input, and then you can do stuff with it. You can output 1s or 0s, or you can read whatever is happening there, or you can trigger some sort of event. Second, the Py4j library supports this communication through the SPI, the I2C, and the UART interfaces. And it's quite important actually, so this is the fourth point that I have here, that it supports managed and unmanaged access. So what does that mean? It means that the managed access is the more Java way that we are used to. We have factories, we have classes, we have objects, we have dynamic arrays and all that stuff, and everything is working perfectly. But in some cases it might be a little bit slow. So in some cases, read as an SPI cases. That's the only case where I've actually seen that it's kind of getting slower. So in some cases, you want to simply jump over that and just use the plain GNI translation to the underlying methods that are placed there in the Raspberry Pi library. So that's why you can use the unmanaged access. And last but not least, there are already extension packages. So if you go on GitHub and you find the project, Pi4j, you can see that there is this extension package there, and there are like a lot of devices already present. So manufacturers or I don't know, contributors that are working there have already the API, and the protocols already developed, so you can use that out of the box. No need just to reinvent the wheel. How can you get started with all this? So I will show you some examples, but maybe you would like to take a picture of this slide if you want to try out something at home. So first of all, acquire a Raspberry Pi 2 and maybe a touchscreen. The touchscreen is quite more interesting. So I have one here, if anyone wants to see it afterwards. So I believe that this is the 2 model. Let me check. Yeah, so this is the Raspberry Pi 2 in a nice Chinese box. And I have a touchscreen. So this is the Pi TFT. Well, it's not the Pi TFT, it's again Chinese replica of the Pi TFT, but nevertheless, it's the same driver, it's the same integrated circuit. It just lacks the brand. That's it. So yeah, first of all, you may want to acquire Raspberry Pi. Second, download the official supported operating system. It's called Raspbian. It's a Debian derivative. You will be familiar with it, from the beginning. Go to Raspberry Pi Org downloads, you can find an image there. Or if that's a bit hard for you, there is also this Noops package. You can download it, boot, and it asks you what kind of operating system do you want to install in a Raspberry Pi. So you just select, click enter, and it will be installed and it will boot immediately on the next start. Third, if you want to do hardware, and I hope that you will want to do hardware. So go to pi4j.com, download the Pi4j library. Directly there it's not present, but there are also build sites for that, and it may be even present on GitHub, I'm not really sure. But nevertheless, just get the Pi4j-core, yeah, here I made a small typo, so Pi4j-core, the jar library, download it, it will be the core thing that you will need. And 4, so you will have all that present, you will have all that installed. Now, how can you actually code on that? So that's up to you, that's pretty much up to you. You can try, and you will succeed actually, to boot the Raspberry Pi and to install Eclipse on it, or NetBeans, or whatever. It will be slow, but nevertheless it will work. But if you want to be more efficient, then go with some other options. So other stuff that I've been using is coding via Vim or Nano, whatever. Or the most efficient method that I've done till now is that I'm coding on my computer. I'm pushing everything to GitHub, and then I'm just pulling, from an SSH there, building, running, and it works. It really is the most efficient method. So quick getting started in order to build stuff. So this is if you compile stuff on the Raspberry Pi. So just invoke javac, add the Pi4j core jar to the class path, manual target directory if you want some, and just place in the input Java files. Now the second thing is more important here. Pay attention to this. So if you run Java applications on the Raspberry Pi which want to access the hardware stuff of the device, so the GPIO header, then you must use sudo, or else simply the application will not be able to tell the operating system in order to export the pins. So just invoke sudo. Again, add the Pi4j core to the class path and the running class that you want to start up. So, hello world. How does a hello world in the hardware area looks like? You take one LED, you take a resistor, and you make it blink. That's the most complicated project that you can do at the beginning. So, first, if you want to connect something, well, not to connect something, if you want to experiment with the Raspberry Pi, and you want to prototype something, then please do not touch or attach pins directly on the GPIO header, because you can very successfully burn your Pi. I mean, there are recipes actually for that, so it's a bit hard, with neighboring pins, but nevertheless, if you take, how was it actually, you take one output, you you set it to be on ground, and then you take VCC, so 5 volts, and you wire them both, and you immediately burn the output. That's it, and you can no longer use it. I haven't burned an output, but I have burned the SPI interface, so yeah, be careful about that. So, first of all, you can use a cobbler cable, so these are these flat cables that have these connections on the end. So you can take one of that, and you can connect one piece, the one part on the Raspberry Pi, and the other one to a proto board, whatever your choice is. And then just use the proto board and connect everything there. So in order to make an LED blink, what will you need? You will need a proto board. You will need this cobbler cable to connect it on the proto board and on the Raspberry Pi on the other side. Some jumper cables, an LED, and a resistor. The resistor in order not to blow up the LED. What do you need to code for that? So this is the managed way in Py4j. We're using the Py4j library here, and you can see we have factories, we have instances, we have all that stuff that we're used to. So first of all, from the GPIO factory, we're getting an instance. We have the GPIO, this is the main controller, and we will use this controller regarding every single pin operation that we can think of. Then we take one pin. So if we want to output something, and if we want to make the LED blink, that means that we need to take this LED on high voltage, say. Now, the Raspberry Pi, the digital outputs of the Raspberry Pi work on 3.3 volts digital logic, so that might be important. So what you need to do is actually take one pin. You need to know the software and the hardware designation of the pin. That can be a little bit tricky. So here, for example, the pin number, the hardware one is 17, but the software number is 0. That's very intuitive, very, very intuitive. So you need to take that pin, and you need to provision it. So that is to export it as an output pin. So this is this invocation here. So you take the pin, you said, okay, now this pin, from now on, it will work as an output pin. Since it's an output pin, you need to define its initial state. It just cannot float out there. You need to have some initial state. So either it needs to be high or low in digital value. So here I say high. So what this invocation will do, it will simply export this pin here, and immediately it will place it on high. But since it's connected here to the resistor and to the LED, and the LED is grounded, then immediately current will flow from here and the LED will turn on. Yay, success. So what we'll do next is we will set the current thread to sleep for 5 seconds, and then we will take the same pin, so it's already here, it's abstracted, it's an object here and everything. We take the pin and we set it on low. That effectively means that the potential here will be set to 0 volts. If it's set to 0 volts, then the current flow will cease from here and the LED will turn off. And then just GPIO shut down in order to let the GPIO to collect this garbage and everything. So again, what will this application, this simple application will do? It will simply light up an LED for 5 seconds, and afterwards it will turn off. That's it. Now, the other side of the hello world, in the hardware section. So what's our world? Now, we made an LED blink, but let's try to sense something that is happening on the outside. And the most simple thing that we can do, the most simple thing that we can sense, is to have a tester, to press that tester, and to sense that exact point when the tester has been pressed. And at that exact point, we should see whether or not the tester is down or up. So it's active or non-active. So again, a very similar syntax we have here, but we have again the output pin here for the red LED. But here we have another pin which is connected to this hardware pin. This is number 18, which on software designation is GPIO01. And we provision this to be a digital input pin. Now, since it's a digital input pin here, we need to set its pin pull resistant. That basically means that when it's disconnected completely, will it be pulled down to ground or will it be pulled up to VCC? So here I say it will be pulled down to ground, so when it's disconnected, it will simply say that the input signal here is 0. That's it. And at the end, since this is an input pin, the only thing that we can do here with the managed access is we can add a listener to it. So this is Java 8 syntax, it looks kind of pretty nice. So we add a listener to this input pin, we get the event, and whenever the event actually that triggered this function, it contains the actual state, which is from the pin. So it will trigger every time. So when you push it down or you pull it up, that event will trigger, but you will have no idea whether or not the input there is high or low. So what you need to do is take the state from the event and check it. And what we're doing here is actually whenever something happens, and if the input state is high, then we take the pin out, so basically this pin here connected to the LED, and we say toggle. So what this application does is, when you press on the taster, the LED will go on, the next time it will go off, the next time it will go on, the next time it will go off. It's that simple. So what can you do afterwards? So you can use this logic and you can make your protocols. You can connect, I don't know, you can use all 16 GPIO pins if you want. You can connect it to a decoder, to integrated circuits, whatever. But it will be very hard because you will need to make this control, you know, on bit level, and that's troublesome. That's problematic. What you would like to do in most of the situations is that you will simply have one additional component and you would like to communicate somehow to it. So you really do not want to know what's happening there in bit level. So you want to connect modules and you want to learn how you can use actually the interfaces in order to communicate with these modules. So I will go through the 3 most important interfaces here and how they can be used in Raspberry Pi with the Py4j library. So the first interface here is the UART, or more known as the serial port, the standard serial port. So what does here the interface says? The hardware stuff, it's basically just 2 pins. We have the transmit pin and the receive pin, and on the other side of the device that you're communicating, you have the same pins. They're just connected elsewhere. So the transmit from your side goes to receive on the device side, and vice versa. What does the serial port actually need in order to communicate? So first you need to set up it. That basically means you need to set the speed, which is the baud rate here, and you need to set the data frame. Now there are standards here, but nevertheless the data frame consists of how many bits go for data, how many bits go for stop bits, how many bits go for parity. So this is for the error checking. It's 801 or 810, I don't know what's the standard actually here. But nevertheless, you can communicate with the device without even specifying these. That's the well-known standard there. How can you use it? So again, we're using the Py4j library here. We have the serial factory. We're creating instance. First of all, we're adding a listener to the serial object. That basically means what should we do whenever we receive data. Then we open the connection. We say default COM port. Default COM port is the serial port which is defined by the TXD and the RXD pins which are placed on the GPIO header, the one that I've talked to you before. And we set it to work on 115/200 bits per second. So what does this application actually does? This short snippet here. So it will initialize the serial port, it will open it, and it will immediately say hi from Raspberry Pi. That's it. And when the device that we're communicating with will send some data, backwards, then this listener here will be triggered, and from the event we can get that data, and basically we will just output it to the standard output, and that's it. So the most simple option of how you can communicate to some third-party device. Now, the serial port is simple, but on the one side it's slow, and on the other side it's not much reliable, so you can actually get cuts. Here I'm saying you can get data, but nevertheless nothing actually says that you will get the data incomplete. You may get it into several pieces, so you might want to add some protocol here. Now, the next interface is SPI. Stands for Serial Peripheral Interface, and it's also known as this 4-wire communication, 4-wire protocol. Now it says 4-wire because basically it uses 4 wires in order to communicate. These 4 wires are here, so it goes for SPI clock, master output, slave input, master input, slave output, basically output from the device or input to the device. These are the pins, and at the end we have SS. This is called slave select. And this is used in order to say to which device currently we are sending data, which one of them is actually enabled. The good thing about the SPI interface that is very fast. It goes several megahertz actually of communication, so it's very, very fast. It also has full duplex communication. Now that's a bit tricky, so if you actually get yourself working with an SPI, there's this little trick there that you need to know, and it basically says that in order to read something, you need to write something. So even if you have something like a device which simply outputs data, you need nothing to communicate with it, you need to first allocate a buffer, fill it with thrash, I don't know, and then write that buffer to the device, and then the device actually will get its output data and it will use the same buffer. So you're actually working with a simple buffer at all time. And the communication that you're doing actually is buffer swapping. That's it. How does the communication with the Py4j actually go? So here, this is not the managed access, and I really advise you not to use the managed access because it's very slow, and it can easily render the communication to be, well, ineffective, and you may not make actually the the device to work at the end. So what you need to do here, first you need to set up the GPIO to initialize the stuff, then you need to initialize the SPI. Here we have channel and speed. Speed, yeah, I haven't really put a number here, there are actually standards for that as well. Now the channel here is a bit more important. There are 2 channels actually on the Raspberry Pi for SPI, but there is only one on the main GPIO header. So this, in 99% of the cases, will always be 1. Then in order to send data, as I said, you need to have a buffer, and you will use that buffer for both reading and writing. So you have that buffer already specified here, and you just invoke this command SPI.read-write. Again, the channel that you're talking to, the length of the data that you need to send and receive in the meantime, and then just executing afterwards in the buffer, you will have the data that you have received. Now here I've marked this with question mark. This basically says that there are some devices there which have this additional pin, which is called chip enable, and that is CE. And some devices actually want to have that connected and pulled down to ground in order to be enabled. So if you make everything and you're completely done with the protocol, but stuff is still not working, then you might be missing this pin here. And last but not least, from the interfaces, go to the I2C, or it can be known as I2C or IIC. Nevertheless, it's all the same. It stands for Inter-Integrated Circuit. Again, it's serial communication, but this time it's addressable. And in my opinion, this is the nicest way, the nicest interface that you can use on the Raspberry Pi. It's simple. It consists only of 2 pins, so you have the data pin and the clock pin. And the best thing about it is that solely on these 2 pins you can attach multiple devices. Every single device that is attached to the I2C interface has its own address, and it can be communicated to by first applying that address. But since this is only one data channel, there is no duplex communication here, so it's only simplex communication. Now, on one single, as I said, on one single set of pins here, you can attach a lot of devices. It's not infinite, it's limited, and it's limited on the addressing space that you have there. Usually when you take a device and you want to communicate with it via I2C, it's up to the manufacturer to say, okay, now if you want to access the device, then use its I2C address, and they can provide you that address. But sometimes that simply is not the case, so they just provide you the board, you have it there, you can connect it, you have no actual idea what the address of the board is. So on the Raspbian there is this very cool utility, it's called I2C Discover. So you just run it, and it scans the entire address space of the I2C, and if it finds a device, it will say you have a device on that address. It has no clue what that device is, but nevertheless it's found something, so it might be a read buffer, write buffer, an actual device, or whatever. And yeah, you will pretty much be familiar with what you're doing from that point on. How can you communicate with the I2C with the PyFJ library? So again, this is the Java way. First we're getting an instance of the I2C bus. There are 2 buses again. We're using bus 1, that is the one on the GPIO header. So first we're instantiating the bus, and then from the bus we're getting the actual device. So here we have the address of the device. We're instantiating it, and afterwards every communication, either read or write, we're using simply this object here. So in order to write data, again, we have the buffer, we have the offset from where we want to start, and the length of the data that we want to transmit. And for reading, the exact same thing, just the opposite way. Now sometimes some devices actually may have 2 I2C addresses. So one to be like to communicate on the one side, the other one to be like a read buffer or something. So you may actually want to specify the exact address where you want actually to communicate those data to or from. Okay, so enough talking, enough code and everything. Let me just show you now an example. So
when you take the device, you specify one address. However, then after that, for read and write, you can specify different address.
Yeah, there are actually devices there, so you attach one single device and it has several I2C addresses on it. That's up to the manufacturer. So basically everything can be done by solely one address, but often enough you will see devices which are not compliant to that. Okay, so one example that I want to show you actually is how you can use an NFC module, how you can connect it to the Raspberry Pi, and how then you can read out NFC tags from it. So the device that I've used here, it's called this NFC module based on PN532. This is an industry standard chip, one of the industry standard chips that provides NFC communication. So this module is, the manufacturer is called IT Studios. I think they're based in China. They're pretty cheap. This board actually here, it has, again, it has this PN532 chip that is actually the core of the device, and two other stuff that are good about this module and why I've actually used it here in order to make this example. So the first one is that it has its onboard antenna. So if you want to do NFC communication, first of all you need to know you have an NFC tag, which is basically something dead. So first of all you need to have some antenna which will provide like a magnetic field. Then this magnetic field will induce some current here. The NFC will turn out to be alive. It will send out some data, backwards, and then you can read that data. Now, in order not to bother with these things like external antennas and stuff like that, you already have an antenna here on board. So basically, you can just use the board, take the NFC, just pass it on top of the board, and it will be read out. That is the first thing that is good about this module. The second thing is the way that we can connect it. So it has two interfaces here. The one is the standard interface, which you can use pin by pin and connect whatever you want there. But the second one is more important for us, and it's more important because it has the same 26-pin layout as the Raspberry Pi, or at least the first 26 pins on the Raspberry Pi 2. So in order to connect this to the Raspberry Pi, you simply just take a cable, a flat cable, 26-pin flat cable, and you connect it directly to the Raspberry Pi. That's it. It has the pin layout, everything is there. What you just need to do here, there are these jumpers that you need to set to work on SPI. That's a little bit tricky. So there's this one trade-off that is present here, and this is something like, well, like the design stuff that I believe the manufacturer here actually decided to do. So only the SPI interface is enabled on this on the Raspberry Pi header. This can be changed though. So some hardware modification, you just take some pin, you break them out, you connect something on the background, and nevertheless you can make it work on I2C or in UART. Now, you will connect that device, you will set it to work on SPI, everything will be there. It has an LED here that will blink green, which says, okay, I'm connected, I'm here. But then how can you communicate with it? Now, this is maybe the toughest part here. And the toughest part here is that you actually need to comply with the protocol that is placed by the manufacturer itself. As I said, the communication from the Raspberry Pi to the devices can at sometimes be pretty much unreliable. And in order to cope with that, you need to add some data mechanisms, so you have error checking, you have packing of the frames and everything. So I'll not go that much into depth here. What you need to know actually is that in order to make the communication to be successful, you need to comply to that protocol. And the protocol is very, very, very strict. It's down to byte level, and it only works if it receives exactly what it's expecting at that moment. If at any point in time something bad happens, something wrong happens, the device resets and you need to start all over. So in order to send data from the Raspberry Pi to the NFC module, first you need to take the header and the body. So this is basically your command, your data that you're sending, and you need to wrap it up in all these things here. So you have preambles, you have starting codes, you have command lengths, you have checksums, you have postambles, blah 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 blah. Everything. Then you send that data, and in order to make sure that the data is being received properly, you need to expect an acknowledgement signal back, and that acknowledgement signal is always these 6 bytes. If you receive them, then that basically means I'm cool here, so you can resume on next. And the next thing that you need to do is to read the response from the device. So that's basically the protocol. And again, reading the response from the device, this is the response that you want to read out. But again, it's framed into a lot of stuff. You have checksums, again you have the start codes, you have the postamble, you have the original command if you want to use it. And yeah, after that, when you will just strip all that, you will have the data that you will need. So how does this actually look like? I've actually used this PN532 model, and I managed to make this device. I call it DoorNFX, which is basically a device that is supposed to be like the controlling unit of an electronic door. So it needs to sit in front of the door. It has NFC module, and the use cases, you take your NFC tag, you pass it through the module, then you enter your key, and if everything is valid, if you're present into a remote database, then the device will open your door. And here, the door is not a door, but it's a green LED. So if this green LED goes on, it means that we're good. If it doesn't go on, then it means that we're bad. So I will just play here. Just pay attention now on the left side. You see there that I'm passing with an NFC tag. I'm entering the code there. It says, okay, accept. And it says first time granted. You can see the LED goes on, which means I'm cool. So that's the door. The door is open right now. And now the second tag, the same NFC tag, but a different code. So that basically means it should not allow us. It says wait, and then it says forbidden. And that's it. So what you need to do here, actually, in order to make this to be the actual device, you take out the LED, you attach transistor-driven relay there, the other part of the relay to be on the electronic door, and that's it. It will work. This device actually connects to a remote server, so you can use that remote server, you can enter credentials there, you can add new ones, you can cut some of the existing ones, and you will have this centralized door access control present in your offices or in your home, whatever. The code for this, along with the instructions to how to make this from scratch, I have already placed there on GitHub. So if I'm on GitHub, Silmedos, same nickname. The project is called DoranFX. Just a little bit of remark, this is a bit deprecated. Now, this is done with the previous implementation that I've been working on, and that is with the Oracle JDK and with the JavaFX that is present into the Oracle JDK 8. Now, this is no longer the case, so just bear in mind that this is a bit deprecated and that it can be done in a much nicer fashion. Now, I'm talking here about the device, and you also that it has a UI and everything, but I still haven't told you nothing about the UI. So where did this thing comes from? So it has touchscreen, and you can touch it, and it works, and it shows interfaces and everything. So the thing that you actually saw here is JavaFX, touchable JavaFX. Okay. So how you can actually use JavaFX on the Raspberry Pi? So first of all, you may want to get a touchscreen if you want to use it on a touchscreen. So again, here I have the PyTFT, or Chinese replica of the PyTFT, is the same thing. So first take that. Then you can see here that the second step I have it scratched out. It says use the JavaFX that is already built into the ARM JDK 8. Now this is no longer there. So from one update, Oracle simply said, okay, we will no longer support JavaFX for ARM devices. And when I asked them, okay, now why do you decided not to do that? They said, well, we actually never did. So it's like a port error. It was working, but we actually never did it. And they just simply decided to not to support it anymore. So from the newest, if you actually get the newest ARM JDK 8, you will see that JavaFX is no longer present. So what you need to do is get the alternative, and the alternative is the OpenJFX. Now, first, when I started with this, I was a bit skeptical because every single experience that I had with OpenJFX turned out to be massive failure. But nevertheless, this time I got surprised, and actually I'm very satisfied with the outcome. So happy, and I think that actually the final outcome that turned out to be is much better than the original implementation that I did with the Oracle with the Oracle JDK. So what you need to continue is first you take the OpenJFX binaries. Now again, one bad side on this entire thing is that you do not have an official source of already built binaries. So you need to find someone who actually builds those, or you need to download the source code and build it on your own, whatever it is. Here, if you want to take already precompiled and built library, you just go to this website. Yeah, that's the most reliable. Yeah, that's the most reliable source actually. It has no domain name still, but nevertheless, this is actually a site. Some guy there actually made its nightly build system, and it's you have fresh jars every morning there. I've tried it out. It's perfectly okay. Nothing illegal there. It's safe. It works. You can download it, and it's doing the job just fine.
Google
So,
Safe Browsing doesn't say anything. Google Safe Browsing doesn't say anything.
yeah, it's good. Okay. Next, you need to build your project, again, using the same class path, everything that I've mentioned you before. And then the fourth step is when you execute it, actually. So this is the different part between the OpenJFX and the JavaFX that was present previously. So the best stuff actually that is present in OpenJFX is that here we have we have Monocle. And Monocle is actually the platform, the windowing platform that is designed to work for ARM devices which have no native support for user interfaces. You know, it's very fast, and it's optimized to work either on a regular screen or on a touch screen, whatever. So what you need to do here is first you need to provide these external directories. You need to say, okay, now use this directory, and this is basically the JFX X directory, which has the OpenJFX binary present there. That's the first thing. Second, you need to specify the platform, Monocle. If you miss this parameter, you will get a runtime exception immediately, and it will say that LensGlass library is not present. So that means that you're missing this, this parameter. And if you're using a touchscreen, as I'm using one here, you need first to say where this touchscreen actually is located. Now, when you're outputting user interface with the JavaFX, at least here in the embedded environment, first thing you need to know is that you really do not need to have an active graphical user interface operating system, let me put it that way. You don't need any X server running up. So you can take a JavaFX application which has its own interface and everything and just execute it through the command line. What JavaFX will do, it will connect directly to the frame buffer, it will render its user interface, it will render a mouse pointer, it will bind all the events, and everything will be there. You really do not need an X server. Even if you have an X server, it will completely mess up with the JavaFX. No, JavaFX will mess up your X server. It will simply overtake the frame buffer, it will render its user interface, and when you will terminate it, the X server will simply not be able to recuperate from that thing. So, there are actually two devices here that you need to know. The first one is the standard HDMI output. So if you want to make JavaFX applications which will render the UI on your screen, on your monitor, then the default one is the frame buffer 0. So this thing goes here, screen fb/dev/fb0. This is your main monitor. If you want to attach a touchscreen, as I did here, this is fb1. So you need to specify that. And if you're using an external one, that means that here you are lacking hardware support for video rendering. So you need to say that it's software rendering here. These are the 4 parameters. Be aware of those because you may not be able to run a JavaFX application without them. And last but not least, be careful because this thing here, has a very low resolution, 320x240, like this. And have precautions because first of all, you have software rendering, second, you have a tinier CPU and things are much slower. So, you know, just don't get thrown around with resources or with complex user interfaces or 3D renderings on everything. How does a simple start frame here looks like with the JavaFX? So, yeah, I will not waste a lot of time here. So simply you create your main application, extend the application. You need to define the width and height. This is if you use a touchscreen actually. Define the width and height. Set title if you want to, I don't know. Define the root pane in order to lay out your components. Set the width and height on it. Then define the main scene. And last, if you want to use touchscreen, first of all, you may want to disable the cursor. Because here, for example, if you saw when I was touching, actually, you saw no mouse cursor whatsoever. If you don't have it disabled, then whenever you click on the touchscreen, the cursor will move onto that point. And last, set the full screen true. You want to do that because there are some over buffering done sometimes, and it may actually get your app, you know, the user interface to run a bit with an offset, horizontal and vertical. That's it. So that was all Raspberry Pi and Raspberry Pi with user interfaces and JavaFX, and you can attach stuff on the Raspberry Pi and it can work, and you have interfaces and you have everything. But what about, yeah?
Do you want to make a break, or when do you want to make a break?
How do you want? I don't need a break if the audience wants a break. Do you want a break?
Yes.
Yeah, they want a break.
Students mostly.
Okay, so they want a break. 5 minutes, 10 minutes, 10 minutes? 10 minutes, okay, so back in 10 minutes.
Има и стикери, как се изкарат. Аз не съм съгласен с това лого.
Като само българите знаят, че България е това така.
Само ти знаеш,
Дадах на някаква стикър, което е хубаво и аз никой не го знае.
Да, обаче здрав.
Это много интересно. Лекциите участват в тази. Имам време да кажа, да иска да кажа. Не някакви толкова. Четири бяха.
Where was I? Okay, so again, I was talking just about Raspberry Pi this, Raspberry Pi that. So what about using a Raspberry Pi and trying to make something nice for your home? So if you want to automate your home or your office, or you just want to make it smarter, so what should you do? So should you just, I don't know, buy 10 Raspberry Pis, connect them at every single place in your apartment, program every single one of them to do what they're supposed to do, and just connect them to a server or something? Well, you can do that. You can definitely do that. But you have two problems. The first one, that it will be much more expensive than it should be. And the second problem is that it will take a lot more time in order to maintain or to set up it, initially. So that's why I want to get you introduced to the wonderful world of ESP 8266 or 8266. Here specifically, I'll be talking about this board that is called Node MCU. I have also one of those here. I have it here, but this is the previous version. This is the next one. So Node MCU. What is a Node MCU? This is the developing or prototyping board. So if you've been working with an Arduino by now, again you have, for example, the Arduino Uno, which again is a development or prototyping board. This is more or less the same thing. It's much Arduino-like. Instead of being based as the Arduinos, which are based on 80 mega processors, this one is based on the one that is called ESP12 or 12E in the newest versions. Again, it's fully programmable, but this is pretty much recent. This is like 3 or 4 months ago. It's fully programmable. Previously, it came in with fully installed firmware by the manufacturer, and it was used as a device that could have connected to the Arduino. But now this has changed. First, the manufacturer actually allowed other users to flash their own software there. Then they introduced an SDK for that, but the language there was kind of bad. And last, there is a much nicer method in order to code for it. So I will explain that later. Much similar as the Arduino, it has GPIO, UART, and SPI interfaces in order to communicate with. Now, For I2C, I'm not really sure. This one definitely doesn't have I2C, but for this one, I'm not sure. Some say that it has I2C, some say that it doesn't. And now, this is all good, but this doesn't differentiate from a regular Arduino. Well, except the CPU actually here. The Arduino works on 16 megahertz or 8 megahertz, the smaller ones. This thing works on 80 megahertz, so it's quite faster. But it has 3 killer features. So the first killer feature is that it has built-in Wi-Fi. Every single one of these ESP variant ESP chips, it has its built-in Wi-Fi. So if you can see here, you can see this wire around here. This is not a wire, this is actually an antenna. And this is the antenna for the Wi-Fi. And it's already built in here inside the chip. That is the first thing. The second killer feature is that this thing is very low on power. So you can actually take one of these, you can code it, smartly code it, let's say, connect it and power it simply by regular batteries, 2A batteries say, it will run. And if you actually connect it, let's say, to 4A batteries and you code it to be smart enough, you can just drop it off, I don't know, somewhere and it will work on its own for 2 months without you even touching it. Yeah? This is the development board, the complete development board. It's the ESP chip actually that matters, and it's even smaller. It's just this thing here. And yeah, the third killer thing is that this is very cheap. So the entire development board costs only $5. You can find it on some Chinese sites, it's already there. That is the board actually, or you can actually buy just the chip if you don't need the development board, and the chip is even cheaper. It costs around $3 or maybe even less if you buy it in bigger quantities. How can you code for that for DSP? So again, I said there are a couple of options here, but the one that I prefer and the one I most warmly recommend to everyone else is that you need to use the Arduino port. So from a recent, release from the Arduino community, they actually released their IDE and said, okay, from now on, we are officially supporting development on the ESP devices, both in the IDE by using the same IDE and both by using the same SDK. So as they made actually a port for the ADK directly to work on the underlying hardware for the ESP chips. How can you actually code for that? So again, you will take the Arduino, you will take the IDE, you will configure everything, and then you need to start working on it. So if you use it, you can use it as a regular node there, you know, you can read some digital stuff out of it, you can write some digital stuff out of it, you can use it as a plain Arduino. But that's really not the trick here, I mean, because you will not get an ESP if you want to solely use it as an Arduino. What you want to do is that you first want to connect this to a wireless network in a way. So you can set it to work in 2 modes. The first mode you can set it is to work as a software access point. So basically you will run it and it will broadcast its own wireless networks. And then you can use your laptop, computer, your iPhone, phone, okay, what kind of phone? And you can connect to it and it will act as a regular access point. It's slower though, but nevertheless it will act like an access point. That is the first mode you can set it to work on. The second mode is you can set it to work as a Wi-Fi client. So basically you just provide the SSID and the password for your home network, the device will boot up and it will immediately connect. And which is even better, it supports most of the protocols there. So it can connect to a non-secure network, it can connect to secure network with the most popular encryption methods that we know. By now, I've only had trouble only connecting it to one router, but with everything else, I really haven't got any issue. And then you will actually write down your code. So besides the available libraries that you have from the Arduino that you can use, or just use the plain Arduino SDK, you can use some libraries that are written specifically for this. The first one, the most interesting one, is that you can use this advanced web server library. So you can make it to act like a regular HTTP web server. And it's not just like providing you with static HTML resources, you can actually program it, you know, with access points, something like Spring MVC, like a stripped Spring MVC. So you take like path methods there, you set on which HTTP method it will react, and then you just say, okay, whenever this thing is triggered, then do that, take this stuff from the request, then add this stuff to the response, and resume on working next. That is one library that you might want to check out. Second interesting library, there's already a WebSockets library out there. I missed writing the name of the library here. It's not bundled with the Arduino, the web server is bundled. This one is not, you need to download it manually. Nevertheless, this can help you to make DSP to run either as a WebSocket client or as a WebSocket server in both. And it works flawlessly, it's very fast. Pretty satisfied with this library, by the way. Next library that you might want to pay attention is called NeoPixel Bus. So this is a library to operate in these NeoPixels that are made by Adafruit, or their standard hardware name, which is called WS2812. And they're basically RGB LED diodes. They're very interesting. I have an example from, with them. Then a next interesting library is called DHT11, and it's a library which connects to temperature and humidity sensors. It has DHT11, DHT22 also, it's quite interesting, and etc, etc, etc. There are always a lot of those. What I've actually noticed is that most of the libraries are already ported, so everything that is kind of working on the Arduino, you can take mostly sure for granted that will work also here. Let me show you an example, so stuff that I've actually done here. So by using an old MCU, the 09 version, so this thing here, then with a strip of WS2812, or as called NeoPixels by Adafruit, which are actually RGB light emitting diodes. And by using the Advanced Web Server library, I've managed to make this Wi-Fi controlled light. So what actually it does is here, first it boots, it connects to a network. I need to hardware, to hard code the SSID and the password for this connection. It connects to the network, and then you can access it by simply using your phone. So you just write down the IP. I still haven't figured out a way of how to actually use the main name there, although there is an option for that. So write down the IP, you get this fabulous user interface here that you can see. It's very fashionable, everything. And what you actually do, you just tap on each color, and then the LED will light up in that color. That's it. So what is done here, I'm using this Advanced Web Server library. This is a static HTML, and it has just bound endpoints to every single color of these. These are again like links, /red, /white, /green stuff. Then I have event handlers, and what each of those event handlers is actually doing is using this NeoPixel Bus library, and it's just setting the output of these LEDs to go to that specific color. That's it. So the entire source code for this, alongside with the instructions on how to build it, alongside with the instructions of how to get started with all these things. So ESP with the Arduino, where to download it, how to get the driver, how to set up the environment, how to get started, then the source code, then how to get installed it. Everything there, it's already there on my blog, so Pancho.mk. I believe this is the last post that I have, yeah. You can see that if you're interested, it will take you a very small amount of time. Every single one of these is cheap. So again, the Node MCU costs like $5. This thing costs like 4 or 5 again. Nevertheless, it's working. But just bear in mind, these are 8 diodes, so if you want to actually make something that will have its purpose, then buy something with at least 60 of those. They're actually modules, like square modules, or stripes, LED stripes that you can buy, rather cheap. Okay, so yeah, this is a bit interesting. Again, it's a node, it's wireless, it's connected somehow, it's tiny, it's cheap. You can say that it's a node that can fit into this Internet of Things, but I pretty much disagree of all that. You have that, but it's working independently. So you can make it to connect your network, you can make it to broadcast its own network, but what you actually need to do is that you need to take out your phone, you need to connect to it, and you need to manually just control it. It's not actually connected on its own to some underlying system, and it doesn't belong to a network, just besides wasting an IP address, and that's it. So you cannot actually think of it as an IoT node. In order to be an IoT node, it needs to make something else. So I will present you my project. It has codename Shejče. Now, I don't know if Shejče is also a Bulgarian word. No? It's not a thingy. A thingy. Shejče. It's a Shejče. Something that you don't know how it's called, you don't know its purpose, it's a bit small, so it's Shejče. Something like that, yeah. Maybe. Yeah, that's it. So yeah, the translation is called Shejče, basically a thingy. That is the most correct translation that I have. So what's my idea behind this project? So first of all, I want to make cheap nodes, and every single one of these cheap nodes to be with its own specific purpose. Second, all these nodes to connect to a Wi-Fi, to a home present Wi-Fi, to connect somewhere. That is the second point. Third, they need to be made very easy to be configured by the end user, frustration-less and everything, so the target end user should know nothing about coding or about hardware or about anything else. He or she just buy the device, get the device, make the device, I don't know, plug it in, and to be able to configure it somehow. Then the user interface, the physical user interface of it, so I'm showing you this, I should be actually showing you this thing here. The user interface of it should be quite simple, so it should have just one status LED and also to be resourceful pretty much. It needs to have only one LED which should be used like a status in order to say whether or not it's working or not, it's connected or not. And if everything goes wrong, then it needs to have a restart button, simply to drive it back to factory default, stuff like that. Then, it needs to be robust, and this, I need to highlight this a lot, because this is maybe one of the most important things here. It needs to be robust. It needs to be robust a lot. Because in this sphere here, in this area, a lot of things can go wrong. You have a tiny device which connects to a wireless network. And just by simply mentioning these two terms, a lot of stuff can go wrong. The connection may drop. The Wi-Fi may be turned off. Or, I don't know, you may have some obstructions. Or the device can restart. Or there will be some huge traffic there on the network. So basically a lot of stuff can happen. And the device needs to be aware of those, and whenever something goes wrong, it needs to try its best in order to re-establish its connection and to make sure that it's still online. That is one of the stuff that it needs to do. And the last three things here, these are more like technical requirements that I put up here. The first one is that I need to use WebSockets for communication. The simple reason is they're fast and they're quite lightweight, definitely that. Second, it needs to have this self-describing initial info protocol. Now this sounds catchy. It is catchy actually. So my idea here is that I want to make like a system, and to make this system at once, and to make a clean differentiation between what is the system and what are the actual devices. And much more importantly, to be able to introduce new kind of devices without even touching the system. So not in order, I make some new device there, and I need to make a new release for the other system in order to make everything work. So this is definitely out of the topic. Every single one of these devices needs to be aware of what it is, and when it's connecting to the network, to a server, it needs to present itself in a nice manner. It needs to say, hello, my name is this and this, I am this and that, and if you want to communicate with me, then let's use this protocol. So I can send you these messages, you can send me these messages, I can send you this protocol and everything. And the target system, the target server, or the target home server, will read all this data and will be aware immediately of what this device is. And it will need nothing else, it will need no software update whatsoever. And last but not least, all of these devices, all of these nodes need to be registered, need to be controlled by a centralized or distributed system. So it can be like a mini home server that you can have installed at your home, or it can be cloud service, I don't know, somewhere at Google picture. Yep.
What about GPUs, about this small thing? How many, and is the same?
You want to have this thing here. It has GPIOs, I think it has only 8. Not really sure, it has 8. They're marked here. Again, it has hardware designations, it has software designations. So if you want to look pretty much into details in that, GitHub, Node MCU dev kit, Node MCU-dev kit, that is the project. You have everything written down there. So how to connect it to an Arduino, you have the designation of the pins, and as I said, it's a GPIO. It has only one analog input. That's very important if you want to do something with analogs, with sensors and everything. It has only one. It has standard UART, it has standard SPI, only one of those. I'm not sure about the I2C. Some says it has, some says it doesn't. Here, I'm seeing I2C pins in some of the options, but again, I'm not really sure. That was your question. Again, it works on 3.3 volt logic, so that's also important. Misha?
На същия слайд. Ако искам да го захраня с
микро-USB.
Аз ако искам да ги разхвърля из къщата, то е много сложно.
Wireless charging?
Да.
Контакт, USB от контакт, с кабел, става сложно.
this is the important thing. So you can actually take just the DSP chip, and it works on 3.3 volts, 2 batteries. That's it. So yeah, I haven't actually worked on these solely by demo. You can take it out completely from here. It has powering pins connected to batteries. It should work. Yeah. But again, micro USB. It's very easy and it's cheap. Okay, so first one of these ideas is how you can actually configure all this. So as I said, you take one of these, you make it or you buy it. I don't know, hopefully. You take it to your home, you connect it, you plug it into, and it boots. But during its first boot, it will say, okay, this is my first boot. I see nothing stored in my memory, so I have no idea actually what should I do. And at that point, the device starts up its own access point. It's open, it's accessible by your phone, and it starts up this advanced web server. So then you take out your phone, you connect directly to the device, you open its IP address. Again, I haven't figured out a way to pass like a name here, but nevertheless, when you connect to the device, when it is the one that is broadcasting the network, then it's always this IP. So just open that IP, and then you will have this interface here shown up. So what you need to do here, you enter just a designation name for the device, the SSID and the password to your home network in order to connect to. And the last field here is the hub location. So this is the server that it needs to connect to. And it's rather open, and you can enter everything here. So this can be a Raspberry Pi placed in the same network. I've actually have an examples for those. It can be a cloud server, or I don't know, it can be whatever. Just as much as it's following the protocol, it can be anything that it's already present there on the network. And last, you just set on what mode does it work. So this is like workaround here. I still haven't figured out a way of how the device should determine what actually is. So I have made 3 out of these 4 already. So you just select what mode it is. Should it be a light? Should it be a switch? Should it be a temperature sensor? And then just submit. And what happens when you submit it is that the device takes all these fields and stores it into its internal EEPROM. This EEPROM is actually like read-only memory, but it's also programmable, so it's not that read-only, it's also write-only at sometimes. But it's persistent. So it means that when you take it out of power, when you plug it back in, that data will stay. It will be there. So you click submit, all the data is being stored into the EEPROM, and the device reboots. And on the next reboot, it takes that data, it sees that there is already some data there present, and it starts to initialize. So the first thing that it needs to do is it will try to connect to your network with the SSID and the password that you provided. So it will connect to the network, then it will try to communicate with the hub. If it gets a connection, then it will say, okay, hello, my name is this one and this one, the device name that you have mentioned there. It will exchange its own initial info protocol. It will say, I'm acting like, I don't know, like an LED. If you want to communicate with me, follow this protocol, please. The server registers it, knows how to communicate with it, and afterwards, the entire communication is being conducted solely by WebSockets. If anything goes wrong during the communication, the device will reboot, or it will just restart the connection. It will not allow itself just to sit there and be dead. So it will always try to connect in a linear method as possible. But if it's up to you, if actually you screw up something, or if let's say you change the password to your home network, then what you need to do is you have a hardware reset button, so you just click on it. It has an event already programmed there, and what it will do is just simply wipe out the EEPROM. So basically it will return it back to its factory state. And then it will reboot again. Again, it will broadcast its own network, and it will ask from you to enter its new configuration, so to re-enter the configuration. Now, this is the side of the modules themselves, but what about the server? Or what about my home mini server, so the thing that I've actually done here? So in order to make a mini home server, I've used, again, a Raspberry Pi 2, and I've used this Pi TFT, the touch screen, or the Chinese replica of the touch screen. Second, I've used the Adafruit Patch Raspbian operating system, so as we've discussed, in order not to bother with updating the kernel, adding new drivers and packages and everything. From Adafruit, they have already a pre-built image, having already that configured, all the libraries are already there, so you just download it and use it out of the box. Everything is connected. For making the software, I'm using JDK8 alongside with OpenJFX for the user interface. And in order to make the communication, I'm using the Java WebSocket library. So I'm keeping things simpler here, I'm keeping them lightweight, so I really do not need a Tomcat running, I don't know, with Java EA there, and using the WebSockets that are present from there. So you just need a WebSocket implementation. And here I'm using this Java WebSocket, which is a standalone library. Now, for this I don't have a source code. The reason is that I'm still kind of working on this. That's for one. Second is I still have no idea where all this is going. I don't know, should I make a business out of it, or I'm not really sure. So for the time being, this is without any source code. So let me show you some demos here. And by demos, I don't mean that I will connect the network here, because something will go wrong definitely. But nevertheless, I have already all of them pre-recorded. So I will show you there. Professionally recorded with my smartphone camera. Okay, so the first thing that I want to show you is an RGB LED light node. So basically the same Wi-Fi light example that I've shown you, but this time it's not working standalone, but it's actually a node of this entire system. How this actually works, so again, this is the a rough schematic. So we have the node MCU, it's used one GPIO and it's connected to these WS2812. This is basically this LED strip here. It has a status LED, it's this one here. And it has a reset switch, it's this one here. These are the main components. Now this is the node. It's powered by micro USB. I have a hub somewhere around here. And this is my home server, home mini server. So again, this is actually it, is this thing here. They're communicating via Wi-Fi's. I mean, the nodes at least are communicating via Wi-Fi, and my home server is connected via Ethernet. That is actually the connection. And how this actually goes, so let's start this thing. So first I'm powering it up, and when it power up, you will see that the LED will turn on, and it will start to blink. Blinking means it's connecting, and now it's connected. Shares data, and you can see that it's already registered there. So now I will try to operate it. So I'll try to change the color. Now this is already the info protocol that is present there. I change the color, the data has been set, and the light turns on. Then I can change the color back, change it again, change it again. Then turn it off. Turn it off basically means change it to black. Yeah, and it's touchscreen, so. Then again, change it back to something and go back. And now you can see that actually the color of the button remains blue. So this is like a short, quick status that you can get directly from your dashboard. You know, how the device is actually, what is the device doing right now. So this is the first example. The second one is a node which is acting like a relay switch node. So you can just take this node. I have that already, have that here too. You can take that node, and on the other side of the relay there, you can attach whatever you want. Well, not whatever you want, something that is pretty much low in power. So let's say like a side light, or I don't know, something that is working on your desk. So this is a switch. Basically, it's a Wi-Fi switch, so you need to provide the user interface to turn the switch on and off. So again, the connection here via GPIO, I'm controlling a relay, and here in order to show you that it actually works, the other side of the relay, which is controlled here, it's connected again to an LED. So basically, it's a wireless LED, but connected to a relay. So again, powering it on, the LED starts to blink, meaning that it's connected. Now, it's already here. It registers the switch, and I say toggle, and then it's been switched on. So the relay gets turned on and off, and the other side, the circuit gets closed. So if I go back, you can see again that the color of the button is green, meaning that it's currently on. If I turn it back, the color then again turns back to red, meaning that it's off. Third example that I have here, now this is an input node. This is a temperature, humidity, and light sensor node. It's based on two sensors. So first I have this one here. So this one here is the DHT11. This is a temperature and humidity sensor. And this thing here, it's pretty much unnoticeable. That is the light sensor. It's a light resistor. That's it. So they're connected to the node MCU. Again, I have the protocol, I have the communication at the beginning. And what this thing is doing, so it's accepting no input data whatsoever, but it's broadcasting data. And it's broadcasting data on every 5 seconds. So in every 5 seconds, you will get a read. And again, the format of these data is determined by this info protocol that I mentioned. So again, firing it up, you will see the LED turning on, direct blink, meaning connecting, registering, and here it is. So I have the sensors. So you open them, just wait a bit because I still have nothing sent, and that's it. So it says 24 degrees, 38%, and by the end it should change to 23, yeah, that's it. And here it shows nothing on the dashboard. I still haven't figured out how to do that, or I was lazy, it was late. So. And last, I tried to make something else, but I didn't succeed it. Well, the point is that my sensor broke. So I wanted to make a device power sensor node, basically, again, an input node, which is kind of like a socket add-on. You plug it into your AC socket, and then you plug some other device, let's say an iron or something. And what it does actually, it senses when the device is on. And it sends that data back to the server. So basically the use case here is you go to work, you're in your car, and somewhere midway there is, okay, did I turn off my stove at home or my oven? Then you just take out your phone and you see if it's off. But again, my sensor broke and I wasn't able to do that, so hopefully I will do it soon. Now these things are already evolving, at least at my side, so this is the latest state. This is the LED light of how it looks like. So the next thing that I'm planning to do, I hope to do soon, is that I will try to make some nice 3D enclosure of it, and not to be on 8 diodes, but to be, let's say, 50 or 60 of those, and to try to make something like a box or something that looks like a thing, and not like, yeah, something that you can hack on. Yeah, and afterwards maybe, I don't know, custom printed circuit board, maybe enclosure, something stylishly designed, and if it turns out to be good, maybe, I don't know, a product. So, at the end, to conclude, just some few stuffs here. So, first of all, JDK8 with OpenJFX turned out to be very nice and very smooth, especially when you're working with the Raspberry Pi 2. I've also worked with these on the Raspberry Pi, the original one. There it was a bit laggy, but nevertheless it was functional. Here it's already smooth and I have no remarks whatsoever. With OpenJFX, I think that every single problem that I had previously regarding user interfaces and making things completely for the Raspberry Pi, it's now completely done in a very nice fashion there. Second, these ESP chips are a massive game changer in the maker communities and also in the IoT sector. So they're very cheap. There are a lot of examples out there. You can buy them easily. So just go, I don't know, AliExpress, Deal Extreme, Banggood. There are also Amazon, eBay. So there are a lot of those. You can buy Node MCUs. You can buy ESPs. There are also a lot of other prototyping boards based on the ESP. You can buy one of those, download Arduino, follow the examples there. They're pretty much easy to start. So yeah, just start hacking. And last but not least here, really be careful. I mean, these are embedded devices. These are slow devices, very low on resources. This is not your desktop i7 computer. So be aware. Pretty much.
The JPine website can run on one of these.
It can, yeah. You can cluster them as well. I mean, you can make like a cluster of it.
Java EE, so it runs fine.
I've made that.
It's slow for me.
Yeah.
Not slow for
Spring with Tomcat and everything. It's slow, but actually it runs. Yeah, so everything is there. Yeah. Yeah. Tomcat with Apache, everything. Just with light TPD, not Apache TPD, light TPD, so just a lighter variant of it. Yeah. Nevertheless, but it works. Okay, so if you have any questions, I believe I can actually take some official questions right now, or just approach me afterwards. Anyone to ask something in front of the audience? Yeah.
About this Node MCU,
Mm-hmm.
you have 10 of them and bind them directly to i7 laptop.
Mm-hmm.
It could be better replacement of Raspberry Pi. This is another approach, but maybe in some cases very effective.
You can connect them to a cloud server again, so yeah, it will be better. Again, so at least the WebSocket library, you just write down a domain name that you want to connect to, and it will connect regardless what it is. So is it local, is it remote, it really doesn't care. If you want to make your own TCP/IP communication or HTTP communication, I'm not really sure about that. Maybe you need to use like a DNS protocol in front of that, if you want to connect something to a cloud.
Could we organize some kind of service on the small board, or just web server kind?
What kind of service?
Can we have some common. So
Can we change the small web server with something about
Yeah, definitely. If it follows the protocol, definitely. WebSocket communication, initial info protocol, if it follows that, if it follows the command afterwards. Basically, just take like a comparison between WSDL in terms of web services and what this thing here is done. So you just need to make your web server which will comply to the language that is provided here, and it will work. Okay, there.
Where do you find $5 price? I didn't find 7.5 is.
No, 532 last price that I got.
Yes, with
AliExpress.
With Porsche, $6.
532 less one. Yeah, or huge quantities. Yeah. Okay, anyone else? Okay, so thanks a lot. And last, I'm Panche MK. That's my blog there. On Twitter, I'm Silumedos. You can follow me. I tweet every once in a while. And on GitHub, some of these examples are already present there, so you can check out the content. So again, thank you for listening.
That's just